Today we're going to be learning about the dynamics of sound waves, and in some cases just waves in general. So in particular, we're going to be looking at how sound waves interact with other objects, how they interact when they move through different media, and a bit later on, how they interact with other sound waves. So to begin with, let's talk about the reflection of sound waves. You're probably quite familiar with the reflection of sound waves, even if you don't know it. An echo is in fact a sound wave that has been reflected. And of course, we'll be learning a little more about that as we go on. It's a basic fact of how waves work that when they go into a different medium, that is, thing to propagate through, then they will split into two smaller waves. One wave is reflected back into the same medium. So we can see that for these little beams of light in the photograph, which are of course a type of wave, they come in from the left and some of them get reflected to the top of the image because they stay in the same medium, air. But the other one is transmitted through the prism, and we can see that some light comes out of the right of the picture. So some light has been reflected from the prism and some light has been transmitted through it. It turns out that if we take the total amount of energy in the reflected wave and the transmitted wave, it'll add up to the same amount of energy that we started with. This means that we don't get any energy created or destroyed. So if the two media are very similar, and there's not much difference between the two media, then most of the wave will just go straight through into the new medium as if nothing had happened. So in this diagram over here, it will be the white part of the wave to the right of the yellow line. So we can see that the wave has just continued straight on through the boundary. But what about this blue reflection? If the two media are very different, then that blue reflection will carry much more energy than the white transmission. If, for example, a sound wave is meeting a solid wall of rock or stone or wood or something, then that medium will be very different to the air that it's been traveling through. So instead of being transmitted into the wall, most of the wave will be reflected from it and produce this series of blue wavefronts. The total amount of energy, if we add up the energy in the reflected wave and in the transmitted wave, is exactly the same as the total amount of energy in the incident wave. That is, the wave that started this whole thing off. So that means that we have three types of waves. We have the incident wave, which is the starting wave that's incident to some sort of barrier. We have the transmitted wave, which goes through the barrier and gets transmitted through the new medium. And we have the reflected wave, which gets bounced back into the same medium from which the incident wave came. Now it's easiest to analyze the reflections of waves if we treat them as plane waves. What is a plane wave? Well, it's illustrated by this diagram over here. In a plane wave, all the wavefronts are parallel. So it means that instead of having curved wavefronts that are spreading out from a single point, we have flat wavefronts, like planes. Remember that in mathematics or in science, plane is a long, flat surface that extends for a very long distance. You might even say infinity. So this means that all the wavefronts are parallel to each other. They're all nice and big and flat, like a plane, which means that we can draw an arrow through all these planes to get a representation of what the wave looks like. It'll just be a straight line. We won't have to worry about it spreading out. Now, when a plane wave meets a different medium, part of it will be reflected. And we can see that in this diagram over here. The wave on the left is incident, and the wave on the right is reflected. Now, the reflected wave will end up coming away from the boundary at the same angle as the incident wave meets it. That means that this angle over here will be the same as this angle over here. In other words, the angle of incidence, that is, the angle of the incident wave, will equal the angle of reflection, that is, the angle of the reflected wave. So it's possible to solve problems about how waves reflect off different barriers simply by using this rule. But for now, we won't talk any more about angles. Instead, we'll go on to echoes. Now, an echo is an example of a reflected sound wave. Remember that sound waves are the ones that we know the most about at this point. So if you clap your hands, then you'll get a sound coming from them, right? And this is sort of a source of sound that's very small compared to the room around you, but which spreads out in all directions. So it's a little bit like a tiny point, that's your clapping hands, creating a sound that spreads out everywhere, right? In all directions. That's why you can hear a clap whether you're in front of or behind or to the side of the person clapping. Makes sense, right? So the waves will spread out and some of them will bounce off obstacles, whether it's the wall of the room or the ceiling or the floor, or if you're outside, it might be something like a tree or the ground. Now, if the obstacle is distant enough, then we'll get a little bit of a delay between the original sound and the reflected sound wave. And that's because sound takes time to travel. It's not instant. We've talked before about the speed of sound. Because our brain processes sound as if it always comes from a single point, that means that it's possible to trick the brain into thinking that there's a different sound coming from a further away point. That is, the brain thinks that the echo is the sound of a separate event. So if we echo a clap off a distant wall, then the brain will hear the nearby clap and think, oh, it's coming from those hands. And then it will hear the echo of the clap, that is, the sound wave for the clap reflected off a distant wall. And the brain will say, there's another clapping sound coming from behind that wall. So it means it's possible to play tricks on the brain with echoes. Now it turns out that we can use echoes in order to figure out information about our environment. And the best way to do this is with a computer, because it can be very difficult to analyze those echoes with our own ears. This is given a special name when we use sound waves or echoes to navigate. We call it sound navigation and ranging, which normally is shortened to sonar. You might have heard the term before. So sonar is often used to detect submerged objects that are underwater. We'll get boats like this one sending out sonar pulses down to the bottom of the seabed. And by listening to the echoes, they'll be able to tell how deep the water is and whether there are any objects submerged in that water. So it's possible to use it to detect submarines or to detect sunken ships and figure out exactly where they are. So sonar uses pulses of ultrasound, which, as we know, are sound waves with a frequency too high to be heard, in order to minimize the outside interference. Most of the outside sounds that might interfere with sonar tend to be in a different frequency. So the computer can measure the delay between the ultrasound pulse it emits and the echo of that pulse. And by looking at the delay between the initial pulse and the echo, it can figure out how far that sound wave must have traveled, and therefore how far away any obstacles are. We'll be looking at a question to figure out exactly how to calculate depth, but that's a little later on. So it turns out that some animals, like dolphins or bats, will use sonar or echolocation as a means of looking at their environment. Bats, for example, spend most of their waking hours in the dark, so they can't rely on their eyes to bring them good information. Instead, they'll send out ultrasound pulses and listen to the reflections. They can use this to find their way even in total darkness. Dolphins do a similar thing, but of course, they do it underwater. And the reason that it's dark is not because they're only active at night, it's because very little light gets down to very deep water. Now we can also use it on a smaller scale. We can also use, that is, ultrasound and ultrasound pulses. So ultrasound imaging is one example of using ultrasound pulses on a much smaller scale than sonar to provide useful information. So ultrasound imaging is a technique that's used to try to image the inside of a human being, or in this case, a cat. What we do is we send ultrasound pulses into the tissue or the flesh of a patient or a cat. Now the sound waves, as they pass through the different media inside a body, will create reflections, and we can pick up those reflections as echoes. So it's a little bit like sonar, but on a smaller scale. Instead of measuring the depth of water, we're simply measuring the depth of different parts inside a body. And this means that we can build up an image of what's inside it. And of course, reflections occur at all changes in medium. So it means that when an ultrasound pulse is sent through the skin, part of it will bounce off the skin and part of it will be transmitted. Part of it will bounce off, say, the blood vessels underneath, and part of it will be transmitted. Finally, some will bounce off the bone underneath that, and some will be transmitted, of course. And so because of this, we're able to build up an image of the layers that are underneath the skin of the body. And the other nice thing about ultrasound is that we can send out pulses more than 200 times per second. Remember that ultrasound has a frequency of about any number above 20,000 hertz. So if we can send a sound wave out at 20,000 hertz, then we can analyze it very quickly with computers. And that means that we can send out another pulse and analyze that one very quickly as well. And if we do this 200 pulses per second, then we can see how the objects that we're imaging will change. Using ultrasound at many pulses per second, we can create real-time images of things that are moving inside a body. For example, we can use ultrasound to look at a beating heart and see exactly how it's beating. And of course, we can also use it to look at unborn embryos or fetuses. We can see a picture of an unborn child over here. And it turns out that in some aspects, ultrasound is much better at, for example, X-rays, at looking at parts of the body. The problem with X-rays is that although they're very quick and they produce a very high resolution image, they're only really good at measuring the hard parts of the body, that is, the bones. It's very difficult to get information on, for example, a beating heart with a single high-resolution X-ray photograph, because most of the X-rays will pass straight through. The other problem is that because X-rays have such high energy compared to ultrasound, they can be unsafe if we use them too much, which means that we can't fire 200 X-ray pulses at someone every second. We can't use them to image very sensitive organs or fetuses. So in these cases, ultrasound tends to be a much better idea. Right, so that's the end of the theory. We know a bit about ultrasound imaging and echolocation and sonar. So let's go on to some questions to test your knowledge.